We will next examine the question of performance of parallel programs. Performance is particularly important for parallel programs because it is one of the main motivations for introducing parallelism in first place. How can we estimate the performance? We can do empirical measurements by running our parallel program on a particular architecture, or we can do asymptotic analysis. Asymptotic analysis allows us to understand how the performance of our algorithm will change when the inputs to the algorithm get larger, or when we have more parallel hardware to use to solve the problem. We will basically be considering the worst case or upper bounds on the performance of our programs. This kind of analysis is something that you have already seen in the case of sequential programs. You basically try to count the number of primitive steps that a program can take as a function of its arguments. For example, if you're inserting an integer into a sorted list of integers, then you know that you can characterize the performance of such program using O notation as O of n. So that means that it takes a linear time in the length of the list to insert a number into it. On the other hand, suppose that we have a balanced binary tree storing also n integers, then you can show that because we only need to traverse one path in this balanced binary tree, that actually the running time is given by the expression O of log n. So let's see how we can do this analysis in our examples. We will first consider the simple building block that we defined previously, namely sum segment. Recall that this function takes the array, takes a parameter p, and crucially the variables s and t that indicate which parts of the array you should process. And it's given by this while loop. Can you find the time bound on sequential execution time of this function? The answer is that the running time is linear in the difference between t and s, because we have an array and we are processing elements from s to t. For each element of the array, we are taking a constant amount of time, which gives us some linear function of the form c1t minus s plus c2. These constants c1 and c2 may be important in practice, but are irrelevant for the asymptotic analysis, which only looks at the rate growth of the function describing the performance. Now let's look at the segment rec function. Recall that this function was computing essentially the same result as a sum segment, but it was doing it by dividing the longer array segments into smaller ones. Here I'm still looking at the sequential version of this function. So when the difference between the bounds is below some threshold, then we will invoke our previous sum segment function that we have just analyzed and concluded that it has the running time O of t minus s. And otherwise, we will compute the middle element of the array and then invoke ourselves recursively with the intervals s to m and m to t. So now we have a recursive function. So the question is, what is the running time of this function as a function of parameters s and t? Observe that this function can be described using a computation tree. For a given parameter s and t, the computation reduces to two recursive calls, one that takes parameters s and m1, where m1 is the middle, and the other one takes parameters m1 and t. And this decomposition continues until the length of our segment is below the threshold. So computation of a recursive function can be described using such tree. This description allows us to also write down and analyze the running time of the function. We can describe the running time using the following recurrence equation. When t minus s is below the threshold, then the work, denoted by w, that this function performs is this linear expression, because it simply reduces to some segment whose cost we have already determined. And otherwise, it equals the sum of the costs of two recursive calls, because we need to compute both of them, and we are doing this sequentially, plus some constant overhead corresponding to these other operations that we are performing, as well as some cost for performing the recursive calls. This m is computed according to this expression here, which I have written here equivalently. Now let's try to solve this equation, or at least estimate the bound, an upper bound for the values of this function given using this definition that we obtained. In order to simplify our analysis, let us look at the special case when the difference between t and s, that is the width of the array segment that we are processing, is of the form 2 to the n times threshold minus 1. So it's just a relatively nice round number for our analysis. And then we'll see that this will also give us the result for the general case. Now what is this n here? N will be the depth of the tree that I have shown on the previous slide. So if we now look at this computation, it will be a tree that has the depth n, and that has 2 to the n leaves and 2 to the n minus 1 internal nodes. This is just the property when you have such balanced tree. So if we sum up the costs in such tree, we'll find the following. Because we have 2 to the n leaves, and each leaf is given by this cost, we will accumulate this part of the cost for our function. So this corresponds to all the base cases taken together. In addition, we will be performing some work in order to decompose the problem. And every time we do the decomposition, we will have some constant amount of work. And how many times do we need to do this decomposition? Well, that corresponds to the number of these internal nodes in the tree. So that's 2 to the n minus 1. If we now look what is constant in this big expression, we will conclude that n is the variable. That's what depends on t minus s. And so we can describe the work performed by our function as a linear function of 2 to the n. Okay, so we have concluded that, in fact, when t minus s is of this form, then the work is, in fact, linear in t minus s, because 2 to the n and t minus s differ by just a constant factor. Now let's just see why essentially the same asymptotic bound applies also for other values of t minus s. For that purpose, let's look at t minus s divided by this constant threshold minus 1, and let's pick number n such that it's the smallest number for which this value is less than equal to 2 to the n. What that means is that 2 to the n minus 1 will be actually smaller than it. Okay, so we pick this value n such that even if t minus s is not the exact power of 2 to the n times threshold minus 1, we find the closest n. So then we observe that our function, in fact, when you give it a bigger value, a bigger parameter, then it does more work. That's easy to see by inspecting the description of this function. And that means that the work performed for some arbitrary parameters s and t will be bounded by the work for 2 to the n. Okay, so this bound applies. Now, all it remains is now to relate somehow this n back to t minus s. And for that, we'll use just this other equation, because we can see that 2 to the n is now also less than 2 times threshold, 2 divided by threshold minus 1 times t minus s. So from this equation here, inequality, we get this other inequality. And this, therefore, gives us the bound on the work of the function for arbitrary s and t. Because threshold is a constant and c phi is also a constant, then we conclude that, in fact, work is linear in t minus s. Okay, so the running time, the work performed by our sequential function segment rec, is linear in t minus s. Let's now look what happens when we add parallelism. Recall that the only difference in the description of the function is that we do these two recursive calls in parallel. But this has a profound impact on the worst case running time. Let us first examine the case where we have an unbounded amount of parallelism. And so let's assume that when we invoke these two recursive calls, they can proceed in parallel without any interference, and that the running time will be, in fact, the maximum of the running times of these two recursive calls. So in terms of our computation tree, we still have the same tree because we are performing the same recursive calls, but the branches of the tree are always performed in parallel. So what is then the recursive equation for the time taken in the case of such unbounded parallelism? We will denote this value by dst. D stands for depth, as you will see. Now, in the base case, nothing has changed. We just have the linear function of t minus s. That happens when t minus s is again below the threshold. But in the recursive case, we are performing these two recursive calls in parallel, so the running time will be the maximum of the costs of these two recursive calls. And there is again some constant overhead. So now, instead of having plus, we have an equation with max. What is the solution of this equation? Let's assume again that t minus s is of this convenient form, 2 to the n times threshold minus 1, where n is the same depth of the tree. As we have seen before, we have 2 to the n leaves and 2 to the n minus 1 internal nodes. Now the value of this function for the base case is just c1 times threshold minus 1 plus c2, because when we perform the base case, the width of the interval is threshold minus 1. Now, as we go one level above, we'll take the maximum of those values, which are identical, so that maximum is just that value itself, and we'll add c3. Okay, so that's why for all the nodes one level above the leaves, we'll have this cost. And as we move up the tree towards the root, all that will happen is that we'll add these costs of decomposition. So when we reach root, we'll have something like c1 threshold minus 1 plus c2 plus n minus 1 times c3. And recall, n is the depth of the tree. So this time, the cost of our function here, this d of st, is in fact bounded by O of n, as opposed to O of 2 to the n. Now, as before, running time, even in this case, when we assume unbounded parallelism, is in fact monotonic in t minus s. So for an arbitrary value of t minus s, by picking the value of n such that 2 to the n minus 1 and 2 to the n are the tightest interval and containing this value, t minus s over threshold minus 1, then we obtain that n is in fact bounded by a logarithm of t minus s. Okay, so by looking at this inequality here, we see that n is less than 1 plus logarithm of t minus s divided by this, which becomes another constant. So when we collect the minus log of threshold minus 1 and this constant 1 from here, we get this c6. Okay, because we still have the bound that applies in this case, which is O of n, and n is bounded by a logarithm of t minus s plus some constant, turns out that this function dst is in fact bounded by O of logarithm of t minus s. So we have exponentially smaller value of this function d. This is therefore an example of a function that with the use of parallelism we can speed up exponentially many times, assuming an unbounded amount of parallel resources. Now that we have seen this example, let's see what is the situation with asymptotic complexity analysis of parallel programs. As you have observed, the complexity depends not only on the sizes of inputs, but also on the amount of parallel hardware resources. And for this purpose, we'll use two measures to quantify the behavior of the program. The first one is work of some expression, some computation E. This is the number of steps that need to be taken by all the processing units involved in computation. And this really corresponds to sequential execution time. It cannot be better than sequential execution time. And that also means that up to a constant, we treat the invocation of parallel of E1, E2 simply as the pair of E1 and E2. So W of E is essentially the sequential execution time of E. What is specific to parallel programs is this notion of depth, which is also sometimes called span. And this is the number of steps that we would take if we had unbounded amount of parallelism. And in this case, for parallel of E1, E2, we'll take the maximum running times of the two arguments. Now, given this intuition for work and depth, what would be the rules for computing it in the case of parallel construct? For work, we need to do both arguments of E1, both E1 and E2. That means that the total work will be the sum of work for E1 and the work for E2. In terms of the tree, if this node denotes the invocation of parallel, then both arguments need to be counted. We add them up. And that means that if we have a tree where each node corresponds to the parallel construct, then all nodes and leaves of the tree need to be summed up. And at each step we have some constant overhead as well. The key difference is now for depth. The depth of computation of construct parallel E1 and E2 is the maximum of the depth of E1 and the depth of E2. What that means is that we compute the amount of work for one branch and the amount of work for the other branch, and then we simply take the larger one. The assumption is that we will be executing these computations in parallel. We're looking at the total time, and what will happen is that whichever computation finishes sooner will wait for the one that takes longer, and that's why we have the maximum here. And of course there's some constant overhead as well, or at least the overhead that we will be assuming that it is constant. So it's in the parallel construct that work and depth differ. In all other respects they behave the same. So but in the case of parallel, if we manage to take some work given by the pair E1, E2 and split it into equal parts, then we will actually finish twice as fast, because in that case the maximum will be half of the sum. For all the other parts of the code where we don't use parallel explicitly, we will assume that the computation proceeds sequentially. So in particular, if we have some operation or function call with arguments E1 through En, what do we need to do? We need to evaluate each of the arguments and then perform the computation given by f. So for work, that just means we do work for E1 and so on, work for En. And then with the values v1 through vn obtained by evaluating E1 through En, we need to invoke function f. And the cost of that depends on what f is. If f is some primitive operation on integers, it's going to be constant. If it's some user-defined function, then we need to estimate the work for that function. And for depth, the computation is exactly the same, because we don't assume that somehow arguments are evaluated in parallel implicitly. If we want parallelism, we have to use the parallel construct or something equivalent. So computation of work and depth is conceptually straightforward, and it proceeds recursively on the structure of the expressions that we are computing. Of course, when we have recursive definitions, we get those recursive equations. Let us just remark that we will assume here that C1 is less than equal to C2, which will make then the depth always be less than equal to work. And this is also to be expected. In most cases, work will be, in fact, strictly more than depth. Now that we have seen how to compute work and depth, let's see how we might use this information to obtain some reasonable estimates for the running time of programs on a concrete platform that has P parallel threads. Now observe that no matter how large P is, we cannot finish sooner than depth of E. In fact, we have defined depth of E to be the amount of work if we had an infinite amount of parallelism. So that's the best case. At the same time, regardless of depth, we cannot finish sooner than the total amount of work divided by P, because realistically, every piece of work will need to be done by some piece of parallel hardware. If we combine these two observations, we conclude that it is reasonable to use the following estimate for the running time of a parallel program in case we have p parallel processing units. We'll take the depth of the expression and add work divided by p. Now we can examine what happens if the amount of computation grows or if the amount of parallelism we have grows. Suppose for the moment that amount of parallelism is constant, so we have a fixed machine or a fixed cluster, but the input grows. So we are considering, for example, larger and larger amounts of data to process. Because p is constant, then parallel program will have the same asymptotic complexity as the sequential one. Namely, this d of e will be not really bigger asymptotically than work of e. And because p is constant, then we'll still have the same asymptotic complexity as w of e. Let's now look at another scenario where as we process larger inputs, we put more resources onto it. Or if we keep the same amount of data but increase parallelism. So as parallelism is increasing, then we can see that this work term vanishes and what is left is depth. And it is important to realize that depth is typically still non-trivial because it involves having to decompose the computation, and it's bounded by the inherent dependencies that we have among the data. And that's why even if p goes to infinity, the running time will not go to 0. It's going to reduce to the depth. Let's see consequences of this analysis for our segment rec example. There we observe that the work is O of t minus s, so it's linear in the amount of input to process, and the depth is logarithmic in the same value. Now we can expand what this O notation means. It corresponds to some functions like this. And now if we observe what happens if p is bounded, but we have varying amounts of input data, then we see that we obtain a linear function in t minus s. On the other hand, if we are increasing p, if we are increasing fast enough as a function of t minus s, then we have logarithmic behavior in t minus s. So if we are throwing more and more parallel resources at the problem, then segment rec behaves logarithmically in the amount of input. Let us now finish by establishing a correspondence with something called Amdahl's law, which is well known in performance evaluation. And it also arises when we have parallel computation. Suppose that we have two parts of computation that need to be done sequentially. So part 1 needs to be done first and then part 2, because part 2 depends on the result of part 1. And let's suppose that initially part 1 takes fraction f of computation, let's say 40% of the time, and that part 2 takes 1 minus f, so the remaining time. Now if we speed up part 2, we speed it up, let's say p times, what happens to the speed up of the entire computation? So if the original computation took a unit amount of time, then the new computation will take amount f, which was the part that we couldn't speed up, and then 1 minus f divided by p, which is the part that we managed to speed up. Okay, so this is the function that we get. And now we observe that this function actually has a plateau. And as we increase parallelism more and more, we get diminishing returns. So even for p equals to 100 and our value of f of 40%, we obtain 2.46 as a speed up. And in fact, even if p goes to infinity, then we'll get just 1 minus f, which in this case is 2.5 speed up. So that tells you that at some point we are facing diminishing returns because there will always be these parts, such as part 1, that we cannot speed up. And that's one reason why we introduced this notion of depth to account for them.